We'll begin this section by reviewing the 10 steps for hypothesis testing. The essential questions are: what are the 4 phases to answering a question with data, and what are the 10 steps to answering a question with data? The 4 phases are broken up into the 10 steps to address how we use science to advance knowledge, or more specifically, how we advance science to answer questions using data. Usually, science forms a question and brings the data to bear, or collects data to answer that question. And informally, we can look at the process as understanding what our data says and form clear questions about the implications. We can state a scientific question as, was this expected, what we saw, or is it something unusual? And then we can compare the data with these 2 choices and decide which one we would like to continue to believe. And then we write down the understanding so that others may make generalizations about the population that was under study. The 4 phases of answering a question with data are stating the question, deciding how to answer the question, actually answering the question, and finally communicating the answer to the question. It is important, whether you're designing an experiment or if the data has already been collected, to go through all 4 phases and all 10 steps. Skipping a phase or a step often means that you will have to back up and review one of the steps or redo looking at the data because you missed something in the initial evaluation. So it is very key to walk through all 4 phases and all 10 steps before simply jumping to calculating your statistic. The detailed steps under phase 1, which is generally stating the question, you need to evaluate and describe your data. You need to review the assumptions associated with your data, and you need to state the question in the form of hypotheses. And we will have 2 hypotheses here, the null and alternative. Once you have evaluated and described your data and stated a question in a statistical fashion, you can then figure out how to decide to answer the question. We'll pick a statistic, that's just a number that will help us address the question. We'll talk about the assumptions associated with that statistic or how random variability can affect it and can then affect our question and how we answer the question. And we'll state a decision rule using that statistic to answer our question. Note that in phase 2 is how we decide between our null and alternative hypotheses. We haven't actually collected any data, or if we have collected the data, in either case, we haven't actually computed the test statistic yet. We make the decision on how we're going to choose between our null and alternative hypotheses before we actually use the data. This is imperative, and we'll discuss that at length. Once we have evaluated and described the data and stated our question and chosen how to answer the question and decided how we'll choose between our null and alternative hypotheses, we'll finally get around to answering the question with our data. Phase 3 is where we will utilize our software to calculate our statistic. We will make a statistical decision between the null and alternative hypotheses, and we will then state the substantive conclusion. So that will be putting the decision back in words or in context of the question. And then finally, phase 4 is communicating the answer to the question. This is where we document or write up our summary of the data using text, tables, and figures. So our goal here is to let the statistics speak for themselves, is to let the data tell you which of the 2 questions or 2 answers you will utilize, the alternative or null hypotheses. These 10 steps will help you so that the data can speak for you. You will not be considering on your own, which hypothesis do I choose? Which one makes more sense to me? You will utilize the data to help you make that decision. Phase 1 of stating the question seems like it's easy. Obviously, there was a question that you wanted to answer, so you went out and collected data, or you utilized data that had already been collected to answer that question. You think that the question is clear to you. However, it is generally not clear in a statistical manner. You have a clear question, but the relationship of the data is tenuous. Maybe you have data and the question isn't entirely clear. Maybe you want to address a question that the data won't answer for you. And so it's very important, especially prior to a study, to talk about what is our question and what is the data that we have or that we will need to collect to answer that question. So where did the data come from? You need to satisfy yourself that it was a well-designed study and that the units of observation in your study are representative of the population that you wish to make inferences back to. Making inference means you'll take the results from your current study and then apply them to the population that you studied in a broader sense. For example, if you determine that a weight loss intervention results in 2 pounds of weight loss and you only studied women, you will then only make inferences back to women. You will not be able to infer that weight loss intervention will work well for men. So what about if you didn't design the study? What about if you're utilizing data that someone else collected? Can you determine the study's methods? Are they clearly defined? Are they relevant? That's actually key. So is this intervention something that people can do on their own? Or are you using data from something that's collected in a very strict manner that won't be applicable to the everyday population? Were there adequate controls in place to assure that data collection was consistent? This is called a protocol. You may have heard that term before. The protocol will outline how the data is collected in a consistent manner across different centers, locations, data collection, or nurses, or coordinators, or physicians. If you're out collecting water samples, there should be a protocol for that. You aren't just going to take any old cup and dip it into a lake. There are certain methodologies you need to follow. So can you define those in the data that you have? And then we talked about if the subjects in the study are representative of, say, cardiac arrest victims. So if you're looking at myocardial infarction, are the patients in your study reflective of those suffering from heart attacks in the general population? And then are the measurements that you're collecting without bias? That is it something that is reproducible, your outcome of interest? Is it reproducible and is it able to be collected without putting bias into the results? So what are the observed statistics? If we refer back to the ECMO case study, they reported that they found that 57 of 90 ECMO patients survived, with their definition of survival being survival to 6 months without any serious adverse effects. So looking for death or a level of function that is appropriate for someone who is suffering from ARDS or acute respiratory distress syndrome. So what are the observed statistics? In the ECMO case study, remember, for acute respiratory distress syndrome, or ARDS, they found that 57 of 90 ECMO patients survived. And remember, survival in that paper was defined as death by 6 months, or, so if they were alive, they needed to be alive without any serious, long-lasting effects. So how are we going to summarize the statement of 57 out of 90? We will use a statistic. A statistic is very simply a single descriptive number computed from the data. In our case, it will be a proportion. After we've chosen the proportion, we're going to review the assumptions associated with that. The next step is stating the assumptions that we're making about the data. There are two concerns here at present. We'll elaborate on the assumptions once we choose our statistic that we'll be using. We need to look at representativeness of the population of interest and that each unit of observation should be independent of the next. Following that, we will state our question. So what in statistical terms is the question? Informally, we want to know if what we observed is different or could be better or worse from what we expected to see. What we expect to see will come from our current understanding of the outcome or from a comparator sample. So when you design your study or when you think about your research question, you have an understanding of what is currently assumed to be true. So we want to know if the data we've collected is actually going to be what we expected or something that tells us that something new is happening. In order to state the question, we need to define a hypothesis. A statistical hypothesis is one that can be evaluated using statistical techniques. So an actual statistical test. We'll talk about conceiving the true state of nature as being either no difference versus a difference. There are two states that we're considering here. A word of caution, your hypothesis is a statement about the underlying population. The hypothesis is not based on your observed data. You form the hypotheses before you collect or analyze the data. We have a null hypothesis. You'll see it written as H with a subscript 0 or just H0. That 0 is the null. So 0 equals null. You'll hear H naught, you'll hear H null, or you'll hear the null hypothesis. All of those, which are the same thing, start with there is no difference. There's no change. There's no improvement. Nothing unusual is occurring. We're going with the status quo. The null hypothesis is the statement you actually want to contradict, and we usually hope to what is called reject the null hypothesis in favor of the alternative hypothesis. We're going to start by assuming that nothing is happening, that whatever new intervention we're studying doesn't work, or it's not better than the current intervention, or that nothing has changed in the pollution in the environment, nothing has gotten worse, or nothing has improved. We're going to assume that any change in our data is due to chance alone. And then we're going to look for evidence to change our mind. So as scientists, we always choose to believe the simplest explanation. That will be the null hypothesis, that our data is just an aberration and it is not sufficient evidence to change our minds. That brings us to the concept of randomness. One of the tenets of statistical analysis is that you should not interpret randomness. Any scatter of your data about what you assumed is just that. Noise. It's just noise. Could be due to some measurement error, could be due to chance, could be due to some slightly sloppy data collection, but it's not telling us anything that makes us want to change our mind from the null hypothesis. What we want to see is there in fact a pattern to the responses that we're seeing that depart from the null hypothesis? Something over and above random error. For example, if you are measuring blood pressure, we would expect that blood pressures will vary slightly depending upon the time of day you collect them, if the person ran in from the parking lot, if they walked up steps. But none of those should be interpreted as something is a meaningful change in blood pressure. Something like that is random error. What we want to know is if we are seeing blood pressure measures far away from what we expect, is there a consistency to that distance away from what we expected to see? So something other than random error. That brings us to the question. So in terms of the null hypothesis, remember that's our true understanding or our current understanding of the data. So we'll state that question by saying that the null hypothesis is less than or equal to some assumed value. And our alternative is that our proportion we observed is greater than an assumed level. We have a null hypothesis and an alternative hypothesis. You will notice that the equal sign is always on the null hypothesis. That's because we assume no change from our current status quo. Our alternative, you'll see it written as HA or H1, is the statement we hope to conclude. This is generally our research hypothesis. Again, it is a statement about the population that is true if the null hypothesis is not true. These are what are called mutually exclusive. Recall in discussion of events about mutually exclusive events, one and only one of these can be true. They are complementary. Either the null hypothesis is true or the alternative hypothesis is true. Since we don't actually know what is in fact true, the reason behind that is we cannot study the entire population of interest. You cannot go collect all of the water from all rivers in all of Alabama. Where would the water go? Where would you keep it? Would the rivers all be empty? So you cannot study an entire population or entire disease population. Therefore, we don't actually know the truth, but we are going to assume the null hypothesis, and we're going to look for evidence to the contrary. So we will not prove the null hypothesis. We will not prove the alternative. We will reject the null hypothesis in favor of the alternative, or we will accept the alternative hypothesis, or we will fail to reject the null hypothesis and continue to believe the null hypothesis. So remove the word prove from your vocabulary in a statistical sense. Once we have evaluated and described the data, assessed our assumptions, and reviewed and stated the questions, we can move on to phase 2, deciding how to answer the question. We'll consider all the outcomes that could happen and assess the impact of standard deviation or random variation in this sample that we've collected. There are 3 steps to phase 2. We need to decide on a summary statistic. We'll start out with summary statistics as proportions. So if the null hypothesis is true, then our observed proportion should be similar to the null proportion, which is denoted as P0 or P0 or P subscript 0. That's the proportion we assume to be happening right now. So if you think about 6% of out-of-hospital cardiac arrests survive, that's our assumed proportion, 6%. If we did another study, we would want to see if an intervention could improve survival beyond 6%. Once we've defined our statistic, we'll reassess that specific statistic. So in this case, a proportion. It could be a mean. But if we are using a proportion, what do we expect to observe if the null hypothesis is true? And what are the amounts of deviation we should expect to see about that proportion? So if the null is true, by the way, we expect to see small amounts of variability. Once we have stated the question, picked our statistic, and looked at random variability in the statistic, we'll state a decision rule. This is going to help us answer the question or choose between the null and alternative hypotheses. We want to have a rule in place before we calculate our statistic so that it is very clear and outlined up front how we will pick between the null and alternative. If you wait until after you've calculated the data or assessed the data, then you're likely to make a different decision based on what you want to happen. Using the decision rule and defining it before you assess the data statistically allows us to be very clear and be able to defend our choice between the null and alternative. That leads us to the concept of alpha. This is one of the most important concepts throughout the course of the semester. It is the Greek symbol alpha, or a script little a. It is the probability of rejecting a true null hypothesis. So remember, we assume the null hypothesis is true. Alpha is the probability of rejecting that hypothesis. The researcher is going to choose that risk, that alpha, concluding that the null hypothesis is false when it really is true. So remember, we assume it to be true. Alpha is the probability that we reject the null in favor of the alternative falsely. The most frequent values are an alpha of 0.05. So 5% of the time we're willing to conclude the alternative when the null is true. Sometimes you'll see 0.01 or 0.1, and we'll talk more about the selection of alpha throughout the course of the semester. The researcher chooses it, but again, prior to conducting the analysis. It is also called a significance level or type 1 error. This is the most important, so type 1 error. We will choose H0 if the p-value that we get from our statistic is greater than alpha. We will choose the alternative if the p-value that we get from our statistic is less than or equal to alpha. So if we see something that tells us that the likelihood we've incorrectly chosen the alternative is very small, we will then conclude the alternative. It is important at this juncture to clarify the difference between p, the proportion, and p-value, which is how we will make our decision. Sometimes we will denote the proportion as p, and sometimes we will denote or abbreviate p-value as p. And you'll often see it written as p less than 0.05. That refers to p-value. Just to make sure that you know when p means proportion and when p means p-value, and those things will become evident over the course of the semester. Once we've made our decision rule, we can actually go about calculating our statistic. We will use our data to determine how our observed data value compares to the expected value. That's p0 in the terms of proportions. And we'll learn about different ways to do this throughout the course. You may have heard of some of them. We'll use a t-test, we'll use a chi-square test, we'll use an f-test. Those are the statistics that we'll be calculating based on our observed p, our null p, and the assumed standard deviation or variation under the null hypothesis. That will give us a statistic. That statistic will give us a p-value. That p-value will help us determine our probability that we're choosing the alternative incorrectly. So when HO is true, the p-value is the probability of the test statistic as extreme or more extreme than the one that we just saw. So again, remember, we're looking for the likelihood or the chance that we're going to choose the alternative incorrectly. The p-value helps us determine that. We will make our decision using the p-value. So based on the information in steps 7 and our decision rule in step 6, we will then choose between our null and alternative hypotheses. From there, we will put the decision back into words in the context of your data. So we won't simply stop by saying the p-value is 0.03. We will need to go ahead and put that decision back into the context of the question in the words of the null and alternative hypotheses, stating very clearly which of those, the null or alternative, we are now accepting. Are we continuing to believe the null, or have we changed our mind and accepted the alternative? And what does that mean in the words that are associated with your population under study? Finally, from there, we communicate the answer to the question. This is phase 4. All of the other phases, 1, 2, and 3, had 3 steps. Phase 4 only has 1 step. It's step 10. It is the most important phase of this process in terms of communicating what you found to researchers, the lay public, and for the media, to put it into journals or abstracts or posters or to give platform presentations. We have a precise question. We talked about how to answer it. We use data to answer it. And finally, we did answer the question. And now we're going to talk about what that all means. Our goal in step 10 is to write a clear and concise summary of your data, what test you did, what the result was, and what that result means. As you can see from the 10 steps, only a small number of them actually involve the data. Your test statistic result and your p-value will be in parentheses in your write-up. They are going to support your conclusions, but they are not the basis of your write-up. They will not be the end-all be-all of what you say. You need to put your decision in context of the data you collected and the larger population you were attempting to study. To be very, very clear, the p-value is not the answer to your question. The p-value helps you determine the answer to your question, and then you must make the inference back to the population at large. We've now introduced the 10 steps to solving a problem with data. Overall, this is called hypothesis testing. Up next, we're going to use the ECMO example with data to demonstrate the use of these 10 steps.